transportation, life sciences, healthcare, agriculture.
Yeah, exactly.
You know, it's a very big topic, yeah? Very, very big topic. And yes, doing something in development and doing research, vis-a-vis then putting that into deployment are two different things.
Yes.
I mean, my last few roles have been in the bank. Trying to push things into production takes a bloody long time. So I hope this works. That's probably not working. Let's see. Okay, so a little bit about me. So I've actually been working in data for just over 20 odd years, and these are some of the companies that I've either worked for or consulted for. So this was my last one, as you all know, and this was my first one, which was back in Manchester after I graduated in 1997, and that's when the head of the IT department walked over to me and asked me if I'd heard of this software. And I said no, and he said, book yourself on a training course, and I did. And Business Objects, if you're not familiar with them, were the leading business intelligence software at the time. They've now been bought by SAP, so it's SAP Business Objects. And then I guess the rest is history. So you know, only a very innocent question by the IT head can change the course of your career. Can you hear me? People can hear me, it's fine.
Everyone can hear you, I think.
So, AI is or can be a very, very complex topic to talk about. So, Mo sort of told me that most of you are beginners and newbies and don't really know where to start when it comes to AI. So, I've tried to make everything pretty straightforward. Hopefully you will understand it. Ask questions, please. Don't sit there and say nothing and then later, you know, you go outside or you go home and you don't understand what I've talked about. Always ask a question, you know, because that will help other people as well who maybe have the same question in their mind and, you know, they need some clarification. So please do ask questions, don't be shy. If you don't ask questions, my assumption is you understood everything, and I've made it really simple for you to understand. If you don't ask questions, if you do ask questions, then you know we get some interaction going, and you know I'd like people to share their views and basically communicate. So AI is a very big topic, and these are all the areas that it sort of covers. And most of this is, you know, what we would talk about in modern technology terms today, as opposed to 10 or 15 years ago. So this is the agenda I'm going to go through. It's different from the one that Mo published because, you know, through consultation and discussion, if I did everything that was published, then we'd probably be still here tomorrow morning, and I'm sure you want to go home at some point tonight. So we'll start with data. Being in data for 20 years, then I've seen the sort of evolution to big data, from business intelligence to data warehousing to data mart to big data, and now we're talking about AI and IoT. So data is nothing new. Earliest records of data, or data being used to track and control business, date back 7,000 years. If you can't see the picture very clearly, this is sort of the Middle East, Syria, Iraq, Iran, Turkey, Kuwait, and this area used to be called Mesopotamia. So, you know, tracking and keeping records of data is nothing really new. But today, how do we use data in business? So, descriptive is what happens. So this is where we look at historic data and we look to see trends and patterns to see, well, why did something happen? Then we go into diagnostic, and then we go into the predictive, which is, well, if this happened in the past, what will happen in the future. And then we go into prescriptive, where, well, if this happened in the past, what will happen in the future, and then what options will you give me? So instead of saying, well, you should do this, it will say, you should do this, and if you do this, these are your options. And if you do that, those are your options. And it might give you several different options. So decision support is very key. Decision automation is sort of the process that we're going through now. Human-centered, where people manually created these algorithms and reporting to decision, and then ultimately a machine-centered and automated platform. So we would call it advanced analytics in most cases, and maybe some of you have heard that term. Modern data is completely different. So this is a report from the IDC. This is a graph from their report. This was done at the end of 2018. So this is their prediction on the annual size of the global data sphere. As they say, I will share the slide so you don't have to take photos. Don't worry. So their prediction, so 90% of the world's data has been generated in the last 2 years, and this is at the end of 2018. Why do you think that is?
The internet, connected devices.
You've all got one. Some of you have got them on your desk in front of you. All because of this. So the world's data has actually grown exponentially. Their prediction is by the end of 2025 we will have 175 zettabytes of data, which will give us a compound annual growth rate of over 61%. How big is a zettabyte? A trillion gigabytes. So it's a lot of data. Just to give you an idea, in that report it says if you download the data to a Blu-ray disc, you would have enough Blu-ray discs to circumnavigate the Earth 222 times, or go back to the moon and back 33 times. So just to give you an idea, that's a lot of data.
Invest in hard drives.
Yeah. So you'll notice at the top I've put velocity and volume there. So volume, as you can see from the report, and then if I give you an idea of the velocity, Singles Day last year, Alibaba, 56,000 payment transactions per second. So it's quite a lot. Yeah. So the types of data which we would call variety, we have structured. So that's in a business you have databases, transactional systems, platforms. We would call that structured. They're in tables, they've got columns, they've got column names. We know what they are. Yeah. From a technical perspective, if anyone looked at the entity relationship diagram, you can pretty much work it out. Semi-structured spreadsheets, XML files, we could put JSON in there, we could put Parquet files in there. Quasi-structured, it's when it starts to get a little bit cloudy. Clickstream data, anything from the internet, because there's no real standard format from web server to web server to web server, or website to website to website. Everyone will do it in a different way. So it's structured, but it'll take time and effort to put it into some form of structure before we can use it. And then we have unstructured text documents, PDFs, images, videos, speech files. That's 80% of the world's data. So if you do the mathematics, 175 zettabytes, and then 80%, yeah, it's quite a lot of work. Veracity. So when we talk about veracity, in data warehousing methodology, we have this concept of single version of the truth. So in business, data in, intelligence out. So the old saying is garbage in, garbage out. Whatever you put into the platform, you're going to get out. You put rubbish information in, you're going to get a rubbish result, right? So we try to work towards a single version of the truth in the business. So if you define a customer in the business, everyone thinks that people external, like they pay for a service, but actually you have internal customers too. HR, marketing, sales, all of different departments, IT. Within IT you have all different streams of IT as well, and they're all your customers. So everyone has a different version of customer within the business, but you need to consolidate that into what constitutes a customer. So that's where we bring in what we call MDM, Master Data Management. So someone senior within the organisation, they have to get a group of people together and say, okay, let's define what our data is. And actually, what does it mean? Internally as well as externally. So, can data be trusted? This is a good question. Data quality, accuracy, integrity, and validity. So how accurate and how truthful is your data set? Data source type, and how is it processed? I.e., where did you get it from? We have highly volatile data, which is something like social media. Sentiment, trending topics change very quickly. So if you look at the news, everything changes very quickly. In the UK, once upon a time, everyone knows, fish and chips. So it used to come in yesterday's newspaper before they decided it was unhealthy for them. And so the old saying was, yesterday's news is today's fish and chip paper. So it was yesterday, this is today. So social media is exactly the same. It changes. And then we have low volatile data. And an example there is weather trends. Change less frequently and easier to predict and track. The infrastructure's in place. The satellites, we know the wind patterns, different climates in different regions. We have seasons. We have the sea patterns. We know the orbits of the moon and the sun, which can impact that. So it makes it easier to predict the weather, apart from today, I guess. So, and this is a programming term. Data is immutable. So immutable in a program, what does that mean? Anyone who's a coder?
You can change it.
Can't change it. Yeah.
Modify.
What would you call it in a program then?
Constant.
You call it constant, yes. Once you define that constant, you're probably not going to change it, right? But you might change it. I'll come to that in the next slide. And obviously data is open to interpretation. So if we go back to social media, everyone can interpret the data in any which way they wish. If we read the news, same principle. But I moved to Beijing. Didn't I say data was immutable? It doesn't change. So in data warehousing and big data, we have this concept of slowly changing dimensions. So in a big data environment, a dimension is just what we would call a column. It's a piece of data. My name, first name, David. That's a dimension. A fact is anything numerical that's related to me. Anything transactional. We have three types. So we update the changes. So actually we've overwritten California to Illinois. Yep. We can keep the historical record. So essentially we've got start and end date, and the end date for the new record is obviously blank. Or we can preserve limited history, right? Original and current. Okay. Type 2 is the most commonly used because we keep history, we keep the historic record. So if you ever wondered why you're being tracked and how you're being tracked, this is how we do it. And then we have value. So I don't know if anyone's heard this term before, datafication. Anybody? No? So this is a good image. So this essentially is showing you the Internet of Things. Everything is becoming connected. From our smartwatches, our smartphones, our autonomous, driverless vehicles. Anything and everything is becoming connected. We can have smart home, we can have smart cities, smart fridge, smart TV, you name it. Pretty much everything is becoming smart, right?
Yeah.
So it's a modern technology trend, turning many aspects of our lives into computerized data and transforming this into information for new forms of value. A good example is Fitbit. So on your Fitbit app, you get presented with this nice little dashboard. Yep. And it tells you your activity, by steps, how many calories you burn, distance, kilometers, and how many minutes you've been active. So 10 years ago you couldn't do that, you didn't know. How far did I run? I guess it's 6 kilometers, but or maybe I have to go on a treadmill just to know I've run 6 kilometers. Yeah? Now we can electronically track it. In the World Cup last year, all the players had a vest, or some of the key players had a vest underneath their football top. They had a chip in football, and that allowed them to produce statistics, how many kilometers they run, how many, all of these statistics. And as a team manager, that allows me to, well, if maybe I need to change the diet, I can change things very quickly instead of, this is my training, and I have this standard format. I can adapt based on the statistics I get from the Internet of Things and datafication. So we call it the 5 V's. Volume, which is the amount of data generated every second. Velocity, the speed. Veracity, which is the trustworthiness of the data. Variety, different types of data. And value. So value is one of the new V's. There used to be 3. There used to be 3, the first 3, and then variety and value have been added recently, or probably over the last 12 to 18 months. Jack Ma has a view. I think we all know who Jack Ma is. This is what his view is. And he said this in 2015. Transformation from IT to DT is making marks a new era for everybody. My view, data can drive or should drive positive change, and understand the past to enable that change. So this is from Gartner. This is what we call reference architecture. So it's a guide. It's not, this is what I should aspire to do. This is a guide, because every company and every business is at a different phase of this data and AI evolution. And you'd be surprised how many companies haven't even started. So typically, this is our internal source systems. We have our centralized systems, image feeds, distributed databases, operational. And this is the new stuff, so streaming in motion. So this is all your videos, audios, and images. So this is where we would source the data from. And sometimes we have to get external data, because sometimes we need to buy some data. Salesforce.com, we need to buy some data from there, we need to buy some data from vendors. One thing that's missing from this, which I noticed, is typically we would land the data first before doing anything with it. In the old days we used to call it staging, then it became a data lake. And some people even call it a data swamp, because there's a lot of stuff in there that's probably not required, but they just dump it in there anyway. So that was actually missing from there. And then we split it off. We've got real-time ingestion, we've got our IoT there. Most companies won't have that, some will. This is just a guideline, like I said. And then we integrate the data. And then we put it into our logical data warehouses, which we would do by virtualization. So we have traditional data management, and then we have distributed processes Hadoop, no SQL. Up here we have our real-time algorithm, and then we move it a step forward into analyze. So We have some policies, we have an orchestration. Orchestration is just probably a routine that says, right, this happens, so I need to do that, this happens, so I need to do that. So this is more of a conductor, so to speak. And then we go into self-service, data services, column storage, in-memory temporary storage, which is, in simple terms, is cache. You know what cache is? Not money, I'm talking about money. I guess the simplest way to put it is that on your mobile, you have this list of recently used apps, and it's there because if you used it again, it will open very quickly. So it's stored in cache, it's stored in memory. Yeah? You can clear it, start again, or you can leave them there. It's your choice. And then this is typically the front end of it. These are your business analysts. You said you did marketing, right? So typically you'd be here. So we can either do it end-to-end from a technical perspective, we can communicate with people, we can build these advanced analytics, or a lot of companies have their own advanced analytics departments that are specific for whichever part of the business that they work in, i.e. marketing, which is your area, right? Yeah. And then we deliver dashboards, visual exploration, smart data discovery, mobile, traditional reporting. So traditional reporting is your sales, your P&L, which has been around for a long time. People still need it, but now we're getting into an area where actually, I'm an analyst, I'm a data scientist, so just give me the data. But obviously I need to be able to trust that data, right? And I need to know that it's clean and it actually has meaning, the metadata is there, and whatever I decide to data mine or do with my data science work, whatever I present to my peers, is true, or as true as it can possibly be, based on current situations. So all of this information that I present here is available online if you know where to look for it. So I will share the slides, and there are links which you can go and actually read the full report and see where this comes from. So this one is actually from the last one they did, which was in 2017. They haven't done one since. From my perspective, it's pretty straightforward, easy to understand. Where were we at ANZ? We've probably done a lot of this, but there's a lot of other stuff that we were doing as well. Any questions so far? No? It's so easy? Very simple.
No, I understand.
You understand it? Good. So this is when I plan to have a break. But since you've got no questions, we can carry on. So, based on what I've just told you, what do we need to do you think?
Changes the data to structure.
And how do we do that?
Data cleansing and data structure.
Any other guesses?
I think the 80% of data, first we should filter the useness data. Yeah. Yes. And then the other part of data we should to try to find its what's the name? To find its feature. We can use this feature to transfer the data to the form we need. Yes. It's like a washing machine. It's to load the data and wash it to the clean data that we need. Okay, I think this is the part.
Yeah, it's good. It's a good start. We're gonna have a break for 10 minutes. Well, we can have a break. So the answer to the question was we need to label the data. So the labeling is very key to our AI algorithms. In a structured format, it's okay. But when we start to bring in the unstructured stuff, and I will use through, stop answering. I will use image recognition through example, because obviously images can be either very simple or can be very, very complex. So we need to start labeling the data, right? So data is nothing new. AI is nothing new either. So this is from PricewaterhouseCoopers. We can go back to 1921. Czech writer, I don't know if you can read this, or Karl Capek, he used the term robot. If we move forward a little bit, who's familiar with the Turing test? Alan Turing. Yeah? Alan Turing. And we've got 3 laws of robotics here as well. And I will do these 2 after this slide. But we have the whole history of AI as the second slide. One thing that's missing from here is the AI winter. They call it the AI winter. So probably around this time to around the early 80s, funding completely disappeared. Because no one believed it. No one believed we could do this. No one thought. So funding actually disappeared. No one wanted to invest. Governments, research, it's completely disappeared. There were a few, but they didn't take off or go anywhere. Before I go to the next slide, let's come back here. One thing which is key here, minimize and maximize. So shrinking disk sizes, exponentially growing capacity help what we do. So is anyone familiar with Moore's law? Moore's law, yeah? The amount of semiconductors on a chip will double in size every 2 years and then he went to 4. Some say that law is dead already. Some say we now have to move into what they call super Moore's law, because CPU architecture as Intel would have it is probably dead. But now we have companies with GPU, which NVIDIA have actually moved into. NVIDIA, their chips were for games originally. You could play games on the computer, everything would be really fast, no lag, cool. They've actually moved into the AI or data sort of area now, and they're marketing their servers as a fully end-to-end artificial intelligence capable server. So if you know Teradata, if you invest in Teradata, they will bring you a nice Teradata box with their name on it. So there you go. So NVIDIA do the same. So most people buy servers, install the software, they get a server from IBM or HP, doesn't matter. But for Teradata and for NVIDIA, they actually bring you a nice shiny box too. And they're not cheap. So this is where we were 1985. And second slide, you can see where we are in 2015. So increase in speed and CPU processes and cheaper disk space allow us to process data very, very, very quickly. Probably 1 million, 2 million times faster than what you can do in your own mind, unless you're a very super intelligent mathematician, of course, or statistician, should I say. I'm not going to go through all of these because I will show the slides again and you can read it at your own leisure and your own pace. But this sort of covers everything when it comes to robotics and artificial intelligence. So, 1942, Isaac Asimov. He was I think he was a biologist of some sort, a doctor in biology, but he wrote books as well. He wrote scientific books about robots. So, he was the first one to use the word robotics in the English language a long time ago. And he came up with 3 laws of robotics. Robot may not injure a human being or through inaction allow a human being to come to harm. Law number 2, a robot must obey orders given to it by human beings, except where such orders would conflict with the first law. It very neatly wraps itself up in the 3rd law. A robot must protect its own existence as long as such protection does not conflict with the 1st or 2nd law. So, why is this relevant? Well, most authors since then who've written any form of science fiction, and you'll see it referenced in a lot of science fiction movies, actually follow these principles. Most. I didn't say all, but most. And then in 1985, it wasn't the 4th law, notice, he actually called it Law 0, or the 0th law. So this was the law that superseded 1, 2, 3. And the 4th law was, a robot may not harm humanity or by inaction allow humanity to come to harm. And so for the best part, this is true. And in reality, we know it's not true. Because we have drones. And I'm sure I don't need to talk too much about that because you know what drones will do. And they're not very nice. Turing test, 1950. So, A, B, and C. C, B, humans, A is computer. What's the point? What was the point of the Turing test?
Make computer like make human couldn't distinguish which one is computer, which one is human.
Yeah, so through a series of questions, interviewer C would ask A and B a series of questions. He can't see who A and B are, whether they're human or computer. And the basic test is to see whether a computer could imitate a human. Yeah. So even if this person asks the computer, "Are you a computer?" it would say no. And same for this one. No. So the person C has to make his mind up. Is it B or A? Which one is the computer? So this was the whole point of the Turing test. And the 3rd one, and this guy is not on the timeline for AI either. So John McCarthy, so together with Turing, they were known as sort of the founding fathers of artificial intelligence. He was the first one to coin the term artificial intelligence. There's some links here, so you can go and have a look at this stuff yourself. So he held a seminar and a conference, and that basically started AI as a scientific field. He invented Lisp, which sadly no one uses anymore. It's been superseded, and that was based on the lambda calculus, which was he brought that to the world in the 1930s. So, classifications of AI. So we can put them into machine learning, narrow, general, super intelligence. Within machine learning, we have supervised, semi-supervised, unsupervised, reinforcement. Cognitive system, I'll come to later. So I'll cover this. This is more important. Here are the abbreviations of what is here. This is a good representation of the algorithms. There are a lot more. But this sort of gives you an idea of what we're talking about. So, a good definition. Focuses on the development of computer programs that access data and use it to learn for themselves. Make sense? Yeah? Yes?
Yes.
Good. Supervised, semi-supervised, unsupervised reinforcement learning. Another definition. So, can apply what's been learned in the past to new data using labeled examples to predict future events, starting from analysis of known training data set. The algorithm learns, produces inferred function to make predictions about the output values. So there's one key word in here that is used a lot when you read about this stuff, inferred, inference. Does anyone know what inference means? No? Ooh, wrong way, sorry. Inference is just basically a conclusion reached on the basis of evidence reason. That's all it means. But you'll see it used a lot in the AI world, inference. Supervised learning, in a nutshell. We have the data, we have a training data set, we have a desired output, somebody's always there if something goes wrong. We have that algorithm, we process it, we get our output. Make sense? Simple? So supervised learning, we actually feeding the output of the algorithm into the system. So the algorithm knows the expected result before working on it. So we know what we want to come out at the end already before we start the process. So if we know both input and expected output, then all we need to do is connect the two together. The training data set guides the algorithm to the expected output. So my training data set will already be labeled. So 1 for a dog, 0 for a cat.
So it's like humans doing the training part, right?
Yes. Don't believe everything you read in the press. Okay. So input data is labeled, so that will be structured data. Here are some examples. If we go back to our advanced analytics, then essentially this has been done, or these types of reporting have been done for a long time. All we're doing now is we're making them better because we can process data faster and we can automate it. So people analytics, info, cybersecurity. So in a cybersecurity environment, my black ops sort of security people, they would be monitoring for intrusions and they would look for patterns of behavior. So if there's a new pattern of behavior, I can get an alert, and I can go and look at it. Financial technology goes without saying that finance is big money. Is everyone aware of the social credit system in China? Yeah? You aware of it? Yeah. So, in the Western world, we have very mature credit rating systems. So if I go and both Alipay and Tencent are both doing it. So how they will decide to agree or disagree is yet to be seen. But the idea comes from, in the West we have very mature credit rating systems. I go to the bank, I want a loan. If I have poor credit rating, they will say no. If I have okay credit rating, they might give me some of what I have asked for. I might want this much, they might give me this much. And if I've got a very good credit rating, they go, oh yeah, you're a great customer, here's the money. In China, traditionally people pay by cash. So there's no way of knowing who, the trustworthiness of the person because you don't know where the money's come from. So social credit rating is a way to try and solve that problem. So now everyone's using Alipay or WeChat Pay to, I don't even carry money anymore because there's no need. And everything is recorded and all my transactions are recorded. Yeah. So the more you use this and the more you link in your, so if I attach my car details there or I attach my mortgage details there into the Alipay and WeChat, then the more they can see about my financial status, they can see my income, what I get paid in the bank, and my disposable income after I've paid all my bills, how much money have I got left to spend. But also it's part of the wider making everyone a responsible and social person within China. The more you are, the more points you get. The less you are, the less points you get. So there's some examples there, and that actually makes up most of the machine learning that we use today. Supervised learning. So unsupervised learning is obviously the opposite. What's different on this diagram to the previous one?
Unable data.
Yeah, and what's the second difference? I can't hear you.
There is no human there to train that.
Yeah, there's no human, and what's the third one?
It says the output is unknown.
Sorry?
It says the output is unknown. Unknown output.
And what's the fourth one, which you've completely missed? Shall I go back? I'll go back.
Okay, no.
No training data.
Yeah.
Yes, there's no training data. No training data. So, what does that mean? Outputs and accuracy, the algorithm are unknown. Algorithm has to find patterns and insight from the data, so it has to make its own conclusion and its own interpretation. No training data to guide the algorithm to the expected output. Input data is not labeled, so that's unstructured data. And therefore, supervised learning is more applicable to real-world scenarios, and that's why it's the most commonly used in the world in business today. So, supervised versus unsupervised learning, example 1. So, supervised, predict a category, classification, divide the socks by colour. So, I already know the colour of my socks. They're red and yellow, I think. Is that red or green? I'm not sure. So yeah, I've already given it the answer, right? Regression is a number. So a good example there is if I feed data and I'm looking for, say, house prices in a certain region, I've already given it the information and it will make a prediction what the average house price is going to be. So here I've given the length of ties and it's going to give me a number in return. Unsupervised. So it looks for patterns and it will use these two algorithms or three algorithms, clustering. So it will look for similarities and go, alright, we've got three. So this could be cat, dog and goldfish. Association, find hidden dependencies. In this example, what clothes do I often wear together? Yeah. And then I'll make the best prediction from what you've given me. Yeah? The best outfit for me. So these are statistical terms: classification, regression, clustering, association, and dimension reduction. Example 2. So in the first one, supervised, I've given it a bunch of pictures with cats and dogs, feed it into the machine will go, these are cats and these are not cats. Yeah. I get classification, then I get real values depending on the information that I'm looking for. Unsupervised learning, I put a whole bunch of photos in, it will put the images into similar groups depending on what it can see in the photo. Similar group 1, similar group 2. So it's not actually telling me these are cats, and it's not actually telling me these are dogs, it's just saying, well, these look similar. So I'll put those there, and these look there. Yeah? So I'm identifying some groups, and I'm looking for anomalies in that data as well. So, why do we have unsupervised learning if we have supervised learning?
Yes.
You're not sure. Good job, I prepared for it. So, we bridge the gap between both, right? So, what I would do is, if with my unstructured data, I can, once I've grouped it into similar groups, then it's easier for me to label it. Yeah? Similarly, once I've got that working, I can then pass some test data, a small sample of test data to unsupervised learning to improve the algorithm, because the algorithm will learn. Yeah? Yeah? So I need to use a combination. So obviously then that increases our size of our training data set here, and then I can retrain this model with our newly labeled data, which obviously then increases the accuracy of the result. So a lot of what I'm talking about, if you know anything about statistics, this should be very familiar for you. Yeah. Very, very familiar for you. And then we come to reinforcement learning. Now this one's it is a little bit more complicated, especially if you go into the principles and the different parts of the algorithm. You can get lost very, very quickly. And if you're familiar with AlphaGo, Google, you know the game Go?
Yes.
The Chinese know the game Go. Yeah, it's the algorithm that beat the champion. And they've actually since improved on that. So I'll come to that in a minute. So we input the raw data, and then, well, we've got all this in the middle, right? We've got an environment, we've got an agent, we've got reward, we've got state, selection of algorithm, and then we've got the best action. And then we've got the output. It all looks very complicated, and you're probably wondering, how the hell does this work? I have a very, very, very simple example for you after this. So we know the mapping from input to output. So for AlphaGo, it's a game. You win, lose, or you draw. I don't know if you can draw in Go, but in chess, you can draw in chess. So I actually know what my expected output will be. I want to win the game. So the agent learns. So in this one, the algorithm is learning to react to an environment. AlphaGo is a game. In a game, you have a boundary. Mathematically and probability, put it into those terms. Chess and Go, there's only a minimum number of moves you can make to win, and then there's a maximum. But then you have all the parameters in the middle, like, well, you have to make your next move dependent on your opponent's move. But if I already know, and I've already worked out where he or she's going to move to, then it makes it very quick for me to make my move. And then the opponent gets confused. In chess, I think they give them, it's 10 to 15 minutes. So when you've made a move, if you've ever watched chess, they press it down, ding, and then the clock starts, and then the other guy, he'll sit and scratch his head, and he's working out all these things, and the clock's going down, and then he has to make a move, ding, and then it's back to the other guy. I'm not sure on Go. I don't know if you have the time limit before your move or next move. Is there?
I think there is.
There is. So obviously, if a computer like AlphaGo can predict all potential moves that the opponent is going to play in a split second, yeah, it's quite powerful. So the agent acts based on the reward for the function. So AlphaGo was trained before it played. I think it actually played the Korean guy 2 years before, and then they updated it, and then they played 60 games on a Go platform, or a Go, and its nickname or alias on the website was the Master, and it played 60 games and it won every one, and then ultimately played the Chinese champion. I think that was 3 games. It got three games to 0. Chooses the best algorithm, so it adapts. There's no one set algorithm to reinforce learning. There's a lot of algorithms, it will choose the best one. And obviously the reward, so if my move is very good, woohoo, that's a reward, right? So we have the classic example for reinforcement learning. We have a dog, we have a biscuit, or a treat, right? So let's apply that to our terminology from reinforcement learning. So the pet becomes the artificial agent. The environment in the scenario, the agent has to face, my owner says, right, I want you to sit for 5 minutes. 5 minutes. Yeah? And it's very difficult for a dog. It's very difficult, especially if you have something like a border collie that has a lot of energy. Sit for 5 minutes, it's a difficult thing, right? So, I have my reward. Yeah? You sit for 5 minutes, you don't get the biscuit. It's very simple. The good behaviour is the resultant action. So the dog will go, because it will work this out over time, you know, I don't get the biscuit because what? I'm not sitting there. But the dog will think, and then, alright, I sit, and then as soon as the owner says, okay, and he gets the biscuit. So it will work it out over time. So it's choosing the right algorithm, yeah? And that is essentially what reinforcement learning is. Put into real terms, put into a real world example. We do it all the time. We could look at a child learning to walk, for example. It's the same principle. Initially the child has absolutely no idea, but sees all these adults and humans around that are walking. No, the child wants to do, but it takes a bit of time. Another good example is, again, I'll use the child scenario. Initially, you teach it that's a cat, and then maybe say what's that, and they go it's a dog or something else, because the child hasn't worked out what makes a cat. It's an animal, it moves. That's all we can figure out over time. We keep reinforcing it's a cat, and then it will start to look for the differences. What makes a cat as opposed to what makes a dog, for example. Animals with 4 legs, but completely different. It looks similar, but not the same. So it's exactly the same principle. So, what is deep learning? We have an input layer, we have a hidden layer, and we have an output layer. We call these neurons. The neurons that are loosely mimicking the network of neurons in the brain designed to recognize patterns. That's essentially what they are. Hierarchical, and all the neurons are connected to each other. So we can have feed forward, where the information is just passed forward and we get an output, or we can have interconnections that go back and forth within this neural network layer. I'll put a picture up in a minute which will show you how complex it can look. So the strength of the signal given in the neuron in the next layer depends on the weight, bias, and activation function, which is the output. So this neuron, what am I going to give to the next one in the hierarchy? Yeah? And it uses obviously mathematical algorithms to update the weights of all the neurons. So in supervised learning, we're doing exactly the same thing, but here we're making it more accurate. Yeah? Because we're actually applying a weighting, a bias, and an activation function to each neuron within the hierarchy, within the structure. And then it starts to learn. So we still have to train. We still have to train it, but over time it will start to learn and it will start to do it itself. This is the difference between machine learning, where you're always going to have somebody there if something goes wrong and need to step in, to deep learning, where it will actually learn and it will correct itself. But again, it all depends on how it's trained. And that's why we have bias. Now we'll come to bias. So it can learn from this, and then it can start to self-correct. These are all the different types of neural networks. And there's quite a lot of them. This one is quite useful, and the one, I don't know if it's on here. No, it's not on there. CNN, which is a convolutional neural network, which is what we are using for facial recognition software. And it's actually not on here, so it's not. This is just, you see the title, a mostly complete chart. So it's not as thorough as it should be. So back to the cat versus dog. Traditional machine learning, deep learning. Feature extraction. So this would be our trainer here. So that watching, everything's working fine or good, something's not right, I need to stop it. So we miss this. The feature extraction on deep learning is actually done as part of the training. So what does it mean? So, very simple in my machine learning. 1 is a dog, 0 is a cat. That's what it's looking for. This is how we train it. There's no great detail here. As you can see, the images are quite complex. And I'm only interested in whether it's a cat or dog. When I apply it to deep learning, then I'm actually looking for the type of dog. This is border collie. This is a tiger. Yes, it's a cat in a sense, but actually it's a tiger. So this is essentially what I'm doing. This is the high level. So in a big data environment, we would call this a drill down. So I'm actually classifying a dog, cat, and then I'm going down a level. Wild cats, house cats. Obviously there's 100,000 or maybe over 100 different breeds of dogs, and then I'm going down another level. So I'm actually getting down to the true detail in deep learning. And that's the difference, because here in deep learning, I can actually extract different parts of this image. So facial recognition. Facial recognition is quite mature, but it's still not 100% perfect. Everyone has a different face. I'm looking for structures in the face, the nose, the eyes, the mouth, ears, different styles of hair, different racial backgrounds. I mean, it all becomes very complicated very quickly when we start to look at humans. So, some examples which you all know, which are all out in the market at the moment. Virtual assistants, Alexa, Siri, Cortana, Bixby. We all know these. Translation, WeChat, Baidu, Google. I think WeChat introduced a new feature on Android yesterday. So when you scan, you normally scan to pay, but you can also select scan to translate now. So you can put your phone at something that's maybe Chinese, and it will translate it for you. I don't know if you've got this on iOS yet, but it was on the updated WeChat, which was available on Android yesterday.
Just English and Chinese.
Yeah, just English and Chinese at the moment. What else have we got? Autonomous vehicles, driverless vehicles. They use deep learning. One story I know about this, so Volvo, which is one of the European car manufacturers, they tested the autonomous vehicle in Australia, in the outback, and it failed. Because, kangaroos, there's no pattern to the way a kangaroo hops. It doesn't like, I do two this way and then two that way, or two this way. There's no pattern to it, it's very random. So they gave up. So if you've ever driven in the outback in Australia, most of the vehicles have these big shields at the front, because a kangaroo can come from nowhere. And then it can disappear just as quickly as that, because the way it hops and bounces is completely random and completely erratic. And the algorithm can't predict. It just cannot predict because there's no pattern to it. So that's quite an interesting story. Chatbots and service bots. Now when you go on the website, you'll get a little pop-up saying, "Hi, how can I help you? Ask me a question." Service bot is a Bank of Shanghai opened a peopleless branch, and you have a little robot on wheels. You can ask very basic questions to the robot. I think maybe some of the banks here do it too. And it's sort of like the first step before they hit the people. If the robot can answer the questions, maybe you leave. It's okay. If they can't, doesn't understand you get a ticket and you wait in the queue. Facial recognition, we've already mentioned. Personalised shopping and entertainment. Amazon, Taobao, Netflix, Youku, Facebook, WeChat, for example. Amazon, one thing they're trying to patent, I don't know if they patented it yet, is when you log on to Amazon, maybe every month you do an order of apples, oranges and pears. But then you look at grapes and tomatoes, because you know you can get it cheaper at your local market, but you still check the price anyway. But you never buy it because it's cheaper at the local market. Right? So you get your monthly delivery of apples, oranges and pears. So what they're trying to patent is, next time you order your apples, oranges and pears, if you've looked at grapes and tomatoes, they will deliver that to your doorstep too, even though you haven't ordered it and even though you haven't paid for it. What's the probability of you sending them back? Because they're on your doorstep. So they're trying to be preemptive based on what you search within the website. Yeah? So this is the smart deep learning starting to work. Yeah? Advertisements works in the same way. So when I've just come back from Europe, and when I was in Nice, I wanted to buy some red jeans. Don't ask me why, I just thought I'd buy some red jeans. And the French like all these sort of paley, pastel-y sort of colours, no red jeans. And I ended up not buying red jeans, I ended up buying red chinos, which are not really jeans. Right? And I searched for them on my phone. And I went and bought them, I found the place. It took me 3 hours in Nice walking around trying to find them, and I eventually found the place down the back street off the main road. And we had a pair of red chinos, not jeans, but they did the job. And then every time I went onto Chrome after that, or Google Chrome after that, what was the advertisement for? Red jeans. Because obviously the algorithm didn't know I'd actually just gone and bought some, because I didn't pay for them electronically, so there was no way and I paid for them in cash. But it doesn't stop the algorithm from just telling me I should order from this place for a pair of red jeans. Interesting, huh? Is there anything more on here? No. So, just to give a summary. So, terms are interchangeable, but in reality, deep learning is just a subset of machine learning, and it's actually the next step in machine learning evolution. So, it learns for itself, whereas what we're doing today is always done, and we have to train and label the data, and it ties and comes comparison. But there are caveats within that. So machine learning uses the algorithms to parse the data, learns from that data, makes informed decisions based on what it's learned. You choose for yourself what you put into that model. What are you looking for? What is your expected output? And if something goes wrong, you step in and you change it, and you get probably the right result. We've nearly finished. That's okay, don't worry. The weather. And it's suitable for small data sets because we have shorter training times and then I can release to production a lot quicker. Deep learning is all of the above except for a few points. So structures, algorithms and layers to create an artificial neural network. Once trained, it can make informed decisions on its own by self-learning correction. So I don't need a trainer anymore, which obviously makes it more accurate. Problem with it is it takes a long time to train it. It's very suitable for large data sets because once it's trained, it can start to process very quickly. But the training takes a long time. It can take a long time. I'll come to that in a minute. So, even though on the diagram we split it into 4 different areas, they're not explicitly separate. So, based on my use case, I choose the algorithm that I need to get the result that I require. It's okay. Most of the algorithms are actually just based on statistical analysis methodologies which are already in place and have been used for a long time. So back to this diagram. So that is what at high level machine learning is. So what's narrow AI? Well, narrow AI is everything that we've just talked about. So this is a horse with blinkers, a racing horse. Do you know why they put blinkers on it? So it doesn't get distracted. So even when it's walking down the street, it's not all it can see is straight ahead. When it's a racehorse, I don't see the horses to my right, I don't see the horses to my left. It's just a straight track in front of me. So it has a very narrow view on the world. We have lots of training data, but it has low generalization. So it only focuses on one task. So I've got image recognition. What's my image recognition for? Facial recognition. So it's very task driven. Yeah. Has no model of the world. We can also call that the old brain. Some people call this the old brain. And the old brain is in terms of evolution. So amoeba, all the stuff that was in the sea, up to the point where the fish decided to come out of the sea and we turned into monkeys, and then apes, and then in the sea we evolved into whales and dolphins. Then everything prior to that, we call it the old brain, because it's very, very, very specific. I should have put a little GIF in here of you may have seen it. There's an iPhone with a fly on the screen going up and down like that. And in front of it is the frog, or it might be toad. And all it does is try to get the fly. It doesn't know it's not real. But that's my view of the world. I'm hungry, I eat flies, and it will sit there all day just trying to get the fly. So that's what we call the old brain. That's what we say. It has a very, very narrow view on the world. Low generalization. Doesn't know much. There is a theory that a duck, when a duckling is born, it will follow the first thing it sees. So if it sees you, it will follow you. It doesn't know you or not its mum. You must be my mum, right? Whatever. So general artificial intelligence and super intelligence. So this is sort of like the next, this probably won't happen in our generation. I'd be surprised if it does. So we call it strong or deep AI. So it has the ability to mimic human intelligence or behavior which is indistinguishable from that of human. So that is general super intelligence. And then obviously super intelligence is when it surpasses human intelligence. To get to that state, AI needs to understand this. And we are way, 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 way from this. So no one's going to put you out of a job anytime soon. You're not going to see this guy walking around anytime soon, because this is all part of human nature. We call it cognitive science. So philosophy, linguistics, which is how we speak. Languages evolve. English is, it used to be, it's derived from, it's actually a Germanic language. So it comes from Northern Europe. But if you go to Germany, it doesn't sound the same because it evolved. Psychology. Psychology is a big business in some countries. Yeah. We all have problems, right? Or perceived problems, possibly. And sometimes we need to go and talk to people to get a different point of view. AI, obviously, is going to be part of that. Neuroscience is definitely part of that. Anthropology is definitely part of that. And linguistics. So we are way, 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 way ahead, way far away from this point in time. That's on the next slide. So we can also call that evolutionary theory. So this is when we start talking about a new brain, a new concepts within artificial intelligence, one of them being causality, for example. So causality is cause and effect. So we do something, something happens, right? So maybe yesterday I ate really hot, spicy hot pot from Turlau or something like that, and then today I don't feel very well. I have a bad stomach. Cause and effect. I know why it happened because I did this yesterday. AI is not at that level yet. So, what's the biggest problem with AI? I touched on this before. Bias. We are all inherently biased. Everybody in this room is inherently biased in some form. Yeah. So, is prejudice in favour or against one thing, person, or group compared with another? Something that some people will think, well, that's not fair. Yeah? And if I'm training my algorithm and I'm inherently biased, then my algorithm is going to be inherently biased too. So the algorithm is always only ever going to be as good as the person or people or team that train it. And it's just something that is in our nature at this moment in time. Over 180 human biases have already been identified. How long before we can eradicate that from humans? Can we? Is it possible? Should be. But how do we do it? This is the tricky question, right? So bias is always a problem. I can give an example of bias. Los Angeles Police Force is a good example. I'm sure Jimmy knows this one. Do you know this one?
I agree.
So they train their algorithm on historic data, right? And once it started working, I mean, outside of the LA police force, if you've spent time in LA, you know exactly what they're like, right? So the algorithm just, well, this is the history. Brilliant, that's what I will do. So if I was a Caucasian or a white guy and I robbed something from the store, here's a $50 fine. You know, I don't do it again. If I was of African origin and I committed the same crime too, I wouldn't get the $50 fine, I would probably get 6 months in prison. So it was actually biased against anybody who wasn't Caucasian or white. If you spent time in LA and you know the history of the LA police force, then you understand what I'm talking about, right? So that algorithm learned from historic data. So that's what the output was. That's the expected output, right? Because that's what it thinks is the right thing to do, because this is what all the people have been doing. So how do you eradicate that? It's a difficult question. Very, very difficult. And how do you eradicate the other 179 human biases? I don't like cheese. I don't eat cheese. Yeah, everyone gives me that look too. That you're a weirdo look. But I don't like cheese. I have no discrimination against anybody who wants to eat cheese, or likes cheese, or wants to roll around on the floor covered in cheese. That's fine for me. But as soon as I mention I don't like cheese, the looks and the comments I get, my local pizza place, I won't say the name because I don't want to put the guy in trouble, because he's a very good friend of mine. And I've been going there for, well, ever since I've lived in Chengdu. And the first time I went in there and said, oh, this pizza with no cheese, he went on about it for 3 hours. Every customer that came in, this guy, he doesn't eat cheese. I was like, man, come on, give it a rest. You know? He stopped doing it now. It took him a while, but now he accepts it and he's okay with it. But initially, he couldn't believe it. You know, what the hell? This is the pizza guy. Right? Someone come in, doesn't want cheese on their pizza. So removing all these biases will take a long time, because maybe we could do it in this room, but then how do we do it on the global scale? Then that becomes a very difficult question. So if we go back to our cognitive science, our algorithm essentially needs to have a worldview. If it hasn't got a worldview, then these things are never going to go away. So, I like this one. I used this one in the presentation at ANZ last year, because I thought it was very funny. So, we have 4 big banks. Yeah? They applied all of their knowledge and training data around football to predict who would win the World Cup last year, right? In Russia, 2018. I love this, it's really good. All these 4, Goldman Sachs, famous, Ing, famous, UBS, Thanks Bank, all famous big financial institutions, train the algorithm to predict the winner of the World Cup. So, Ing, who do you think they came out with? Who do you think the winner would be?
Netherlands.
Netherlands?
Germany.
Germany? Anyone else want to have a guess?
Netherlands wasn't qualified, was it? But it's a Dutch band, that's why I said.
Yeah. They predicted Spain. Woo! Goldman Sachs. Who do you think they predicted? Come on, you all must have watched the World Cup. You always know a little bit about football, right? Or soccer, depending on where you come from.
Britain.
Britain?
They're not from the UK.
We don't have a UK team. It's Scotland, Northern Ireland, Ireland, Wales, and England.
England.
And there was only England in the World Cup, because Scotland haven't been in it since 1984, I think. Pretty rubbish. Goldman Sachs predicted Brazil. Brazil, strong team. Danske Bank. Brazil too. And UBS. Germany. Yeah. Who won it? France won it, right? Yeah. So, funny, right? All these big financial institutions wanted to prove their AI capability, and not one of them came up with the right result.
Did they publish the confidence of their prediction?
Did they, sorry?
Publish like the confidence of their prediction?
They didn't publish it, and I think Goldman Sachs updated theirs after when it got to the semi-finals, there's only 4 teams left, right? So, well, I've got a 25% chance of getting it right. But initially, this is what they came up with, and France were the winner, because I guess they didn't take into account that...
They had pretty high confidence, and they put it in the Wall Street Journal.
Yeah.
Like 90% plus confidence.
They published it, yeah, so, yeah.
Only no publicity is bad
Team was
publicity.
among the
so
top
never
4.
mind.
None of this team was among top 4.
Yeah, none of them were in the top 4. Yeah, none of them got to the semi-finals. Brilliant, right? So, yeah, don't think, like I said before, don't think that you're going to be out of a job anytime soon, because you're not.
I couldn't have predicted it better though.
Pardon?
I couldn't have predicted it better though.
Well, I guess there's probably parameters that they didn't consider as part of their training algorithm. France being the very close team, the team plays pretty much across Europe. They're young, they're fit. Football can be very unpredictable at times, but it can be, at the same time, it can be very predictable. So, how do you train the algorithm? How do you train the model?
How to pick what you want to predict.
Yes. This is my expected output. Maybe the main team on this development were Spanish. Maybe these were Brazilian, and maybe they were German. We don't know. We don't know who they were. Right? So, what do you need? And this will go for anybody, if you're a startup in business or going to start on an AI project. So, Robert Baden-Powell, any idea who he was? No. You know the Boy Scouts? He was the founder of the Boy Scouts. He was? Yes, he was. Yeah. After the Second World War.
I'm just saying this, I'm not a Boy Scout.
I didn't say you were, but learn from history, right?
Yeah.
That's what algorithms do. So, obviously, what's your business case? What's your use case? What problem are you trying to solve? Yeah. I think that goes without saying. Get the buy-in. Whether you're a startup or an entrepreneur, you need your investors. Whether you're internal, you're working at a company already, you need to sell this to the stakeholders. Because if your stakeholders are of a certain age, probably they have no idea what you're talking about. Yeah? They read a lot on the internet, but it doesn't mean they think about it and see how it can be used for their own business. Now this is very important, right? A diverse and socially aware team. So diverse can mean anything. Young, old, male, female, doesn't really matter. Chinese, English, British, Scottish, Thai, American. You need a diverse team because you need to bring into your algorithm the social awareness. If you have more social awareness when you're building your algorithm, at least you can mitigate the risk of bias. You might not mitigate all of it because from experience, it's normally the strongest personality in the room who says this is what we're going to do. And the most senior. Yeah, I'm paying for this. This is the way you're going to do it. Right? So you have to get their buy-in. They have to understand the core concepts around bias and how we build this type of. Obviously, source the right data. I think that goes without saying as well. Because dirty data will always introduce bias into the algorithm, which then when you present it, like the 4 big banks with their predictions for the World Cup, everyone just went, yeah, really? you start to lose the trust of people, your customers, and like Jimmy said, it was in the Wall Street Journal. How many people read that edition of the Wall Street Journal? And then looked at these 4 banks and went, maybe I should move my account somewhere else. And obviously correctly label the data. And this is very key to me. Process the data, model the problem. Obviously, it's very key that you validate the output. And that could be the investors, it could be the stakeholders. And then deploy. Very simple. So, before I finish, 3 laws that I mentioned earlier have actually been updated. So this guy, he works in the University of Bristol, and he's a professor of robotic ethics. But you didn't even think there could be such a job. But there is. So he's proposed a revised 5 laws, not 3 laws, or yeah, it's still 3 laws with a 0th law. It's still 3 laws. He's provided or proposed revised 5 laws. So European Network for the Advancement of Artificial Cognitive Systems. Right? So there's a body who are looking at the next step of the evolution, yeah, to general artificial intelligence, yeah. And you'll notice the subtle differences here. So yes, it still can't harm anybody, but all right, we've got a little cameo there. National security, yes, that's okay. Yeah, so should be designed and operated as far as practical to comply with existing laws, fundamental rights and freedoms, including privacy. Right? Privacy is a big issue in big data, in machine learning, deep learning, and artificial intelligence. Privacy is becoming an issue. In Europe, we now have the law GDPR. Yeah. So the European government has decided to try to start doing something about the privacy laws. Right? Robots are products. Yes, that's true. They should be designed using processes which assure their safety and security. Yeah? So they're products, so we should look after them too. Yeah? It shouldn't be a one-way thing. They are manufactured artifacts. They should not be designed in a deceptive way to exploit vulnerable users. Instead, their machine nature should be transparent. Right? So in my robot image, I'm using data from Star Trek. If you're familiar with Star Trek, Data, right? He's very, he's on the good side of the world. Yeah? And he's logical, and he will give you the good options or the good answers. Yeah? If I want to look at the opposite side of that, are you familiar with the Aliens films? Yes, we have the ones called David, yeah? And he's very Machiavellian. Right? So he's evil, right? So, yeah. So this is the way we should manufacture them. We should manufacture them in a good way. Yeah. And then obviously, this one is key. If you have a robot and it does anything that's really bad or outside of these parameters, you're the one who's going to get in trouble, not the robot. Yeah. So these are still under discussion. Nothing's been written in stone. It was just a proposal in 2013. Yeah. So, if you remember the reference architecture I showed you before, almost exactly the same picture, except we have this process in place here. We were mentioning about the cleaning of the data and the transformation and the normalization. It's all been added here. Yeah. So it becomes part of the big data ecosystem. Yeah. Everything else on this picture is pretty much the same. Externally, we've got APIs here. If I'm GCP, Google Cloud Platform, this would be my view to my outside world entry point. Yeah, I can go on GCP, I can load data on GCP, I can run my algorithms on GCP, and then I can get results. The financial institutions in the UK are now, by law, being forced to release APIs so external parties can have access to customer data. So it's quite interesting how things are starting to evolve. But again, this is just a guideline. How companies implement it obviously is dependent on their budget, their current infrastructure, skills that are available on the market, and all of those parameters that come into place. This is the the best I could make it without. There's a link here. So you can open the link and zoom in on it a bit closer, but there is a lot of companies already in this market, because data and AI are essentially the same thing. AI is just data-driven decision making, and data has been used to make decisions for a long time. We used to call them decision support systems before we got into business intelligence and data warehousing. So, you know, they walk hand in hand. So there's a lot of companies already. You can click on the link, and then you can open the image, and then you can zoom in. I mean, I couldn't make this any smaller. If I made it smaller, it would look silly. And that was about as big as I could make it. But at least giving you some idea of the number of players in the market already. But what does that mean? Plenty of opportunities. Plenty of opportunities. Right? Don't really focus on these two. Skill gaps. So this is overall. Globally, we've got a 68% skill gap or labour shortage in this industry. China, it's 51%. The US, 68. UK, well, yeah, 73. You want to go to the UK and make money? Start learning your AI and data now. Is the pound still strong? I'm not sure. I don't think it is. Brexit. Brilliant. But yes, there's
British accent introduces bias.
Well, that's if you believe. I consider myself more of a global citizen because I've worked in 3 different continents, and I've met a lot of people from a lot of different backgrounds and a lot of different cultures and a lot of different countries. So sooner or later you're going to move to a global citizen. So this is from a Deloitte report towards the end of last year. So plenty of opportunities if that's what you want to do and that's your interest. Sooner or later it will have to become your interest, because companies are actually making this a part of their strategy. I mean, data enabled comes first, which was the first architecture I presented before. Once they're data enabled, then we can start looking at the algorithms and artificial intelligence. Yeah. So here it says believe. Within 3 years. For some, it's going to take longer. For others, they're already there. The Googles and the Amazons, they've been doing this, but they've got big budgets. They can do things quicker. Yeah. But small to medium businesses, and obviously some banks, they're not there yet. It's a lot of work. It's not something you can do overnight, or do in a month, or do in 2 months. And that's it. Any questions?
Yeah, questions.
I have one.
Yeah.
But I will go last. Any other questions?
Well, that was an hour and 34 minutes. Well, I said 90 minutes. Not bad.
Are there any other questions?
This lady has a question.
Yes.
I have a question, but my question is more about myself. The thing is, I'm going to study statistics as my master program, but I'm concerned that if it requires a PhD degree to be a data scientist in the US.
In the US, no. Not as
And,
far as I'm aware, no.
and there are some certain limit in the career path if I just have a master degree, just statistical master degree.
Statistics will take you a long way to being a data scientist.
Okay, thank you.
If you, as you're doing your statistical study, do some technical stuff, learn Python.
Okay.
Learn the code.
Learn the code. Python is the go-to language at the moment for...
Is statistical program the proper program if I want to be a machine learning engineer?
Most of the algorithms are very mature already, and Python provides those libraries that you can add in, depending on what your problem is and what you're trying to solve. But you know, if you're doing the theoretical statistical analysis stuff, learn to code at the same time, you should be a very good data scientist. Yeah?
Thank you.
Yeah.
Yeah, it's all stats and linear algebra.
Yeah, that's what it is. Linear algebra. And what's the perfect numbers?
Yeah.
Okay, thank you.
I've been reading some books about machine learning algorithm, and I found most of the algorithm they have been written in Python. Are there any other languages also that we can write those algorithms other than Python?
R used to be the go-to language, yeah? But over the last 18 months,
What's the reason for our losing the?
Microsoft bought them, I think.
No, I think so. I can answer.
Yeah, sure.
So Python about 6 or 8 years ago became the language of academia. So you started seeing a lot of academics begin to use Python. Slowly after that, R emerged as a language for mathematicians and statisticians. That is a derivative of Python. And so currently, most of the innovation that is going into AI is still very much from upper academia. And therefore, their language is being pushed into the ecosystem. I think over the next 10 years, my personal opinion is that you'll start to see corporates take over that innovation. And you'll start to see better languages, maybe C, maybe Golang, other languages that corporations are using more to bite into Python's market share in AI, because corporations want to use their own tools. But as long as you have, like in Chengdu just 6 months ago, I met the principal scientist for Amazon, the principal AI scientist for Amazon. But she's also a professor at Caltech. So all these big companies that are hiring these data scientists, they're getting them from universities. In most cases, they're getting them as like tenured professors. And so that influence is still very evident. As soon as corporations start to take over and bring that in-house, and universities have produced enough AI scientists that they become like Dave, right? They have the academic background and then they stack on top 20 years of experience that Dave has, then corporations won't need universities anymore. Universities will have to go invest in new. And at that point, the language that corporations pick, it may, like I said, I listed off a few languages earlier, will then take over the AI language market share. What do you think?
Yeah, I totally agree. I mean, Python's going to be the language for probably 5 to 10 years now. Obviously, the research is quite mature in quantum computing as well, and at some point that's going to come into, academia as well. Quantum computing is still a grey area, still up in the stars. It's still pretty much with the physicists and not the scientists, not the mathematicians. So at some point you're going to see that starting to take over. That'll be the next thing, because to get the general artificial intelligence, to get this cognitive worldview, what we're doing today and what deep learning can do at the moment has a limitation. So we have to find a way to bridge that gap. Is quantum computing the answer? We're not sure yet. We don't know, because that's pretty much still in research. No?
Can I add on to that topic?
Sure.
I think we're still missing a concept here. We are talking about data science, data scientists, and machine learning engineers. We're talking about scientists and engineers. These are two different types of people, right? And as for when we're talking about research, we're talking about developing algorithms or finding new algorithms other than convolutional neural networks or RNNs or whatever. We're pushing the boundaries. Python has the features that you can easily model and represent your thoughts into computerized programs. So that's very convenient when you trying to push the boundaries. However, machine learning engineers are trying to apply the algorithms, the the research results into production, into applications. And that's totally a different area. And we're looking at not the performance of the algorithms in terms of accuracy, precision, recall, stuff like that. We're talking about concurrency, bandwidth.
All of
talking
those
about
things,
speed, right?
All of these things come into
Yeah,
play,
all of these things.
especially in a big organization. Yeah.
And obviously, Python is not a great tool for that. So that's why, TensorFlow comes along, and TensorFlow JS, you can use JavaScript to utilize what.
So basically, what the end result was just a basic report, split by sales region across the UK, and all it said was, this is a good customer, we need to keep him. This guy, he's borderline, but this guy, oh my God, he's having our cars for 2 years, he's hammering them up and down the motorway, he's not maintaining them, he's not looking after them. So when the contract finishes, I have no resale value, the car is worth nothing because the guy or the company hasn't maintained it. So what do I get in return? I get nothing, right? So either if they're really, really bad, they're giving them, the sales guy will go and try to change the behavior, and if they didn't, we just terminate the contract because they weren't adding value, and they were losing us more money, and that's a profitability report. We then took it to another level because the cars needed maintaining, so they need to go to garages to get fixed, have the service. So you start to look at the garages. Why is this guy over here, we're in the same town, he's charging more money for this part than this guy over here? Why is that? Because at factory price, the part costs the same amount of money. So why is this guy charging more? Do we need this guy? You get into these sort of conversations, and then you go into the suppliers, and you go into the supply chain. So that was the first one I architectured and built. And then after that, I'm here today. So, I've been very lucky, very fortunate, but once you are in this industry and doing this job, then you can start to predict yourself. Because after a while, you don't need the data. Because the data is all about the people. At the end of the day, the data is all about the people. So, what books have I read? Bill Inman. He's seen as the, you probably don't want to read this, it's quite old. He's seen as the grandfather, the father of data warehousing. So I got into a conversation with him before I left the UK. He sent me a signed book and I read it. But the architecture, the concepts are still pretty much not changed, but obviously the technology's changed since then. So you need to keep abreast of what's happening with technology, the changes, the upcoming changes, and how can you apply that in the company that we work for. I can't believe you didn't know I left Ames. I'm still there. But yeah, I don't really read books per se. I'm reading David Deutsch's books at the moment, and he's seen as the father of quantum computing. He's the head of physics at Oxford University. And he's published a few books, so I'm sort of reading them. And he sort of talks about a lot of things from philosophy to history to, he even talks about Turing test as well. And he's a physicist, so you have a mathematical side of things, you have a physicist side of things. So Stephen Hawking talk. These are good ways, because these are the top of their jobs, right? They're known globally, people respect them, so you have to look at it from their point of view and read their material. That gives you a good idea of possibly what's going to happen next. And I guess a lot of it is just experience. You can't beat an old experience at the end of the day.
You should write books and you'll buy.
I should write a book, yeah. Probably won't get published in China. No, but I have to remove all bias, so it would be very neutral, so it would be okay. But yeah, and talk to your peers. I know people I used to work with. My first project manager, he had a PhD in astrophysics, and he was working in IT. He couldn't find a job. He couldn't find a job, and he couldn't find a job that would pay him the money because it's a sad fact but true, you know? Because most of these guys, they end up just doing research and working at universities, and if they don't get the funding, then there's nothing for them. And if that market is already there, or the vacancies that are already filled up, then. But he was a very smart guy, and I learned a lot. He was my project manager. I'm like, why the hell are you doing this for? And then they explained it. You know? I've met people who are in IT who are geologists. They come from all backgrounds. You know? This is the whole learn to code ethic. You know, it doesn't matter where you come from or what your specialist subject is. Sooner or later, you will have to know technology when you go for an interview, because that's the way that the world and the market is evolving towards. If you don't know anything about technology, unless you're obviously just going to work in a cafe and make coffee all day, then that's okay. But for big enterprises or big companies, sooner or later you will have to know something about it. It's not going to be, I'm a business guy or I'm a techie guy, we're going to be one and the same. Right? If I don't understand the business, then how can I write the code and do my research and do my job? So, I know you're not from tech, and I suggest you start to learn something. Python is a good start.
Thank you.
Connect up with this guy, do something.
Yeah, actually there's a website called Coursera.
They're from